record. Okay, today you have the third math learning project activity due tonight. And then homework 6 is due Friday. We're going to do this super secret number activity, but I want to do one question first, and then we'll come back to the super secret number activity. So this is 13 from the homework. And the reason I want to do this is because it talks about the second derivative with implicit differentiation. So I want to do this example because I didn't have a second derivative one on the notes on Monday. So I want to do this one and then. Okay, so we're going to say x cubed plus y cubed is 1. We want to find the first derivative and then we want to find the second derivative. So x cubed plus y cubed is 1. When I take the derivative implicitly, I say 3x squared plus 3y squared. What do I have to put here? dy dx, yep. Equals 0, because the derivative of 1 is 0. Okay, so to find the first derivative, I'm going to solve for this dy dx. To solve for dy dx, I would subtract 3x squared and divide by 3y squared. I did that all in one step. So negative x squared over y squared. Well, I don't know why I turned that upside down. Okay, so that's dy dx. That's what I would put in this box here. I don't have to do that simplifying. You could put the negative 3x squared over 3y squared in that box. Doesn't matter. You can put either one in there. Okay, now I need the second derivative, right? So to take the second derivative of this thing, I have to take the derivative again. I can either do the derivative from this line over here, or I can do it from this line over here. If I do it from the one on the left, which rule am I going to need to use here? The product rule. Yeah, if I do it from the one on the left, I'm going to need the product rule because I have 3y squared times another variable dy dx, right? If I do it from here, this one on the right, what do I need? The quotient rule, right? I mean, both are yucky. It doesn't matter, right? You can choose whichever you want to do, but you'll have to use either the product rule or the quotient rule. I'm going to do it with the quotient rule because I feel like we haven't done that in a long time. So to find the second derivative, I'm going to do the derivative of this thing. So to do the derivative of this thing, I'm going to do the quotient rule. Quotient rule says bottom y squared times the derivative of the top, negative 2x, minus top, negative x squared, times the derivative of the bottom, 2y dy dx, over the bottom function, y squared squared. The tricky part is that you can't enter dy dx into the answer box, right? So what are you going to put in here for dy dx? Yeah, whatever this was, right? So here in this piece where it says dy dx, you're going to enter that negative x squared over y squared piece, or the negative 3x squared over 3y squared, doesn't matter. Negative 2xy squared. This guy's going to be a plus because I have two minuses. 2x squared y times dy dx, negative x squared over y squared, divided by y to the fourth. I can simplify that if I want to. I can just enter it in like that. Doesn't matter. But I can't enter it in when it has dy dx in it. Okay, so I'm going to pause the recording. We are going to play the super secret number. Inverse functions are the undoers. Exponentials and logs are inverse functions. Sine and arc sine or sine inverse, those are the undoers, right? Basically, if you have f of x equals y, then the inverse goes in the opposite direction. The inputs are the y's and the outputs are the x's. So if you're going to take the derivative of the inverse function, it turns out that you can just use the derivative of the original function at the value of the inverse. So basically what this says is if g is the inverse of f, then the derivative of g is f prime, the derivative of f at g of x, okay? So this is just a rule that works for inverse functions. So this says calculate g of 3 and g prime of 3, where g of x is the inverse of this function here. It turns out I don't even need to know the inverse, right? I just need to know, to find g of 3, I need to know what x spits out 3, right? And to find g prime of 3, I do 1 over f prime, the derivative of this guy, at 3, right? Because, or at g of 3, after I find that there, okay? So if I'm using these rules, g of 3 is the solution to this equation. G of 3 is the solution to this equation because g is the inverse of f. So 3 is the y value. 3 is the undoer. Okay, so how would I solve this? I would put in my calculator and find where it crosses, right? I know solving a cube is really hard, right? So I'm going to open up Desmos. I'm going to graph f of x is 1/4 x cubed plus x plus 1. And then I'm going to graph y equals 3. And I'm going to look for this x value right here. 1.365. Okay. So right here at 1.365, this function f spits out a y value of 3. Did everybody see that? I know I want the y value because it's the inverse. I know I want the y value because g is the inverse. So 3 is the y value. This point is 1.365, comma 3. That means if x is 1.365, f of x, so g of 3 is 1.365. Because they're inverses, they just undo. They flip-flop the x's and the y's. Okay, so I'm trying to use this formula right here. To find g prime of 3, I'm going to do 1 over f prime of g of 3, or 1 over f prime of, what's g of 3? 1.365. So do you see I never have to know what the inverse function g is? I just need to know how it relates to the function f that they give me. So all I need to compute is f prime, the derivative of this guy, at 1.365. I got 1.365 by saying f of what equals 3. So I solved this equation, f for 3. So I did that in the Desmos. I just graphed that. I graphed 3 and I found out where they were the same. So that was the Desmos here. Here was my f. Here was my where they're equal. So when x is 1.365, y is 3. That means in the inverse, when x is 3, y is 1.365. The inverse switches the x's and the y's. Okay, so to find g prime of 3, I need to know f prime of this number. So first I have to find f prime of x. How do you take the derivative of this guy? Just do it. Yeah, what's it going to be? 3 over 4, bring the power in front, x to the second, plus 1 plus 0, right? So f prime of 1.365 is 3 over 4 times 1.365 squared plus 1. I'll put that in my calculator. 3 over 4 times 1.365 squared plus 1 is 2.397, let's say. And that's what goes here. So g prime of 3, oh, I gotta squeeze it in, is 1 over 2.397. .417. So I found a whole bunch of things about the inverse function without ever finding its equation. Okay, I found a whole bunch of things about the inverse function g of x without ever finding its equation, just by knowing things about f of x and by knowing this rule about the derivative of the inverse. Okay, so we're going to talk about the inverse trig functions. And with the inverse trig functions, there are ways to show what these derivatives are. We're not going to do them. If you're interested in that, I'm happy to show you and direct you to some places where you can see that. But we're going to add the inverse derivatives list rules to your list. So if you have your derivative rules, they should be on there. They're near the bottom. We're going to do them with x's, but you should always be thinking about the chain rule happening, okay? So you should always be thinking about the chain rule. Maybe we want to do these with u's instead of x's. Okay, the derivative of sine inverse. This is sine inverse, not sine to the -1, right? You could also call this arc sine. Sometimes you see it written as arc sine. It turns out is 1 over square root 1 minus x squared. Cosine is almost exactly the same except with a negative. And that turns out to be the rule for all of these. The secant is 1 over, we put this x in the front, x squared minus 1. The cosecant is the same with a negative. And then tangent inverse is 1 over x squared plus 1. Cotangent is the same, but with a negative. So what I want you to think about when you do these derivatives is that you should always be using the chain rule. Anytime this is not just an x in here, you're going to put all of that stuff there instead, right? And then what are you going to multiply by at the end? The derivative of that stuff, right? Anytime this is not just an x here, you're going to put all of the stuff in there and you're going to multiply by the derivative of that stuff at the end. Okay, so the chain rule should always be happening, kind of like natural log, right? The derivative of natural log is 1 over x. But if it's natural log of a whole bunch of stuff, it's 1 over that whole bunch of stuff. So the derivative of tangent inverse is 1 over x squared plus 1.
Is that an absolute value?
That's an absolute value of x, yeah. But if the stuff inside is not just an x, it's 1 over that whole bunch of stuff squared plus 1. Okay, so let's try to practice using these rules. Yep. So we're going to be flipping back and forth a bunch to use these rules. Okay, so we're going to start by taking the derivative of cosine inverse of 3x. So the derivative of cosine inverse of 3x. Remember, the stuff inside here is not just an x. So when I take the derivative, I'm going to use the rule 1 over, what's the derivative of cosine inverse? Look back. -1 over square root 1 minus, instead of putting x here, what am I going to put? All that stuff, 3x squared times, what am I going to put at the end? Times 3, because the derivative of that inside stuff is a 3. We did use the chain rule, yep, because the stuff inside is not just X. So we use the chain rule. You should always use the chain rule, yep. If you use the chain rule and you don't need it, the worst that happens is you put a ×1 at the end. And there's nothing wrong with multiplying by 1 as many times as 1. Okay, how about this guy? Derivative of tangent inverse. Derivative of tangent inverse is 1 over a whole bunch of stuff squared plus 1, right? What goes in this yellow box? 2x squared, all squared, right? Times, what goes at the end? 4x, the derivative of that inside stuff. And again, you don't have to simplify. If you want to, you can, right? You could write this as 4x over, when I square this guy, I get 4x to the 4th plus 1, but you don't have to. Okay, one more. Derivative of secant inverse. The derivative of secant inverse is 1 over absolute value of stuff, right? Times square root of stuff squared minus 1. The yellow is all that stuff. 5x to the 6th. 5x to the 6th. Times 30, the derivative of the inside, the derivative of that yellow piece, 30x to the 5th. So maybe up here when you're writing your rules, you say cosine inverse of u is -1 over square root 1 minus u squared times du. And tangent inverse of u is 1 over u squared plus 1 times du. And secant inverse of u is 1 over absolute value of u, square root u squared plus minus 1 times du, right? So think of it as a u with that du, a derivative of u at the end.
Yeah, when we did the first problem, what was the answer to G of 3? Was it 1.365 or 1 over 1.365?
1 over 1 point, no, 1.365 went inside this derivative here.
What was G of 3?
G of 3 was 1.365. Yes. So the first answer, I guess we had two answers. G of 3 was 1.365 and G prime of 3 was this 0.417. Okay, let's look at this one. Find the derivative of sine of cosine inverse of 4x. How many like pieces does this function have? It needs two chain rules, right? The outside most layer is that sine, and then the layer inside of that is that cosine inverse, and the layer inside of that is the 4x, right? So first I'm going to take the derivative of the sine, then I'm going to multiply by the derivative of the cosine inverse, then I'm going to multiply by the derivative of the 4x, right? So I have those three layers. Okay, so what's the derivative of sine of something? Cosine of something. That inside stuff doesn't change. Times. So I did the sine, so I imagine I'm like covering up the sine, right? I use the sine, and now I'm taking the derivative of cosine inverse of 4x. How do you take the derivative of cosine inverse of 4x? -1 over square root. Yeah, -1 over the square root of 1 minus the whole bunch of stuff squared. What goes inside this parentheses? 4x, whatever was inside there before goes inside there at the end. Times 4, because my inside most function is that 4x. So this first piece was the derivative of the sine. You keep all the stuff that's inside it the same. The second piece is the derivative of the cosine inverse. You keep all the stuff that's inside it the same. The third piece was the derivative of that very inside stuff, 4x. So we get that 4 there at the very end. We can simplify this a little bit, right? Because cosine and cosine inverse are inverses of each other, right? And so when you do them one after the other, what should happen? They should cancel, right? When you do cosine, cosine inverse, or cosine inverse cosine, it should cancel, and you're going to be left with just this 4x. So you can do that simplifying, you don't have to, but that's the whole point of inverses, is that they cancel. And that'll make your entering into infinity better, easier. One was a cosine, one was a cosine inverse, right? When you do one after the other, they go away. Yeah. And leave you with just the inside stuff. It's kind of like multiplying by 5 and dividing by 5. They do each other opposite. Okay, last one. I want you guys to try this one. What is the equation of the tangent line to the curve y equals sine inverse x at the point where x equals square root 2 over 2? What is the equation of the tangent line to the curve y equals sine inverse of x at the point where x equals square root 2 over 2? How do you find the equation of a tangent line? Use a slope. How do you find the slope? With the derivative. And then what else do you need? The point. We have x. How do you get the y? Plug it in. Okay, go for it. Let's say 5 minutes. Oh, we don't take that long. Might need your calculator or your unit circle or your thinking caps. One of those on. Square. Yeah.
So this is the equation
Of f prime, f inverse prime.
so replace
But we replace the inverse with g. Because we're just calling g inverse. So this after the -1 is the notation that we use for inverse. It's a little bit easier to read if we call g the inverse.
oh, so
So we
instead of
replace
F,
all the f -1s with g's.
Correct calculators in degrees or radians.
I would do it in radians.
What I got, put it in.
Yeah, can you write it in
Radians.
terms of pi? It's tough, eh?
So this you got, so this you got is
We solved this equation in the, we solved that. equation.
this the y value of g. is-
Yes. How's it going? Did everybody find the derivative? What do you guys get from the derivative? 1 over square root 1 minus x squared. And then you can plug it in, absolutely. It says, oh, because you only can put the square root on the top, too, not on the bottom. Yeah, your square root's on the top and the bottom. Only put it on the top too, not on the bottom too. Y prime, you told me is this. Okay, so my slope is gonna be. Okay, how do I get my point?
Plug in the square root to-
Plug
the
in.
to the original.
Yeah,
We don't have a base.
That's
That's always confusing.
what do you mean? What do you mean a
The
base?
formula is y minus y equals m times x minus x
Yeah.
plus b. What's the b?
Oh, no, you don't need the plus b if you use that formula. Yeah. We're gonna find the, if you use the y equals mx plus b formula, then you need to find the b. If you use the y minus y is m times x minus x, then you don't need the b. Yeah. What'd you get for this one when you solved sine inverse of square root 2 over 2? Pi over 4. So remember, sine inverse is the angle whose sine is square root 2 over 2, right? So you find the angle whose sine is square root 2 over 2. It might be easier for you to do it in degrees and then convert it to radians, whatever your favorite method is, or remember it from the unit circle. So my point is going to be square root 2 over 2 comma pi over 4. What'd you get for your slope? Let's see, this is 1/2 square root 2. Yeah. No. Maybe. Let's see. Let's go slower. 1 over square root of 1 minus, when I square root 2 over 2, what do I get? 2 over 4. 1 minus 2 over 4 is 2 over 4, right? 1/2. 1 divided by the square root of 1/2 is flip it and multiply. Which is square root 2. Yeah, that's what 1.414 equals. Yeah.
The inverse would be of two answers.
So inverse sine is defined very particularly from negative pi over 2 to positive pi over 2. So we would only pick the pi over 4, but we could actually have an infinite number of angles whose sine is square root 2 over 2. Yeah, but we always pick the one in quadrant 1 or quadrant 4. Okay, so I'm looking for my equation of the line. I have this point, square root 2 over 2 comma pi over 4, and this slope square root 2. I don't know how much leeway Adfinity gives you if your numbers are like rounded. I don't know. You'd have to keep a lot of decimals, I guess. Y minus pi over 4 equals m square root 2 times x minus square root 2 over 2. Okay, if I distribute this guy, I get y minus pi over 4 is square root of 2x minus 1, because square root 2 times square root 2 is 2, over 2 makes 1. Add pi over 4, So square root 2x minus 1 plus pi over 4. That was yucky. If you put decimals in there, make sure this square root only goes over the 2, not over the x. The x is not underneath the square root. Okay, so announcement reminder. Announcement, I decided this morning, because 10% of my students are out with COVID, that I will be giving the midterm online in Gradescope next Wednesday during class time. Okay, so instead of coming to class to take the midterm in person, you will prepare yourself to submit it in Gradescope. It will be a tiny bit different than your handwritten assignments. So normally in your handwritten assignments, you do everything on paper and you upload one PDF, right? In this assignment, there will be questions where you have to upload PDF and questions that you answer directly in Gradescope, kind of like you do for Affinity. So it will be part short answer, show all your work, and part multiple choice, just enter your answer. So what you're going to see is that it's going to ask you to upload a couple of different times. So what that means is you can make one PDF and upload that PDF over and over again, or you can make them individually and upload them as you complete, whichever you want to do. I'm going to give you, like normally our class is 75 minutes. I'm going to give you 90 minutes because of that like uploading time, okay? So it will open Wednesday at 12:30 and it will close Wednesday at 2, just as if you were in class to take it. That means that if you don't start until 1:15, you're only getting 45 minutes. If you don't start until 1:30, you're only getting half an hour, okay? So it's good if you upload. That's next week on Wednesday. Next week on Friday, we will have no class. My sister's getting married. I'm flying to New York. Right, it's a second wedding.
This is second.
Yeah. The other reminder is that I'm in the AEC today until 3 o'clock and Friday until 3 o'clock. So if you need any extra help, come join me in the AEC. It's a ball of fun down there. You have your math learning project due tonight, or due Friday. All right, see you guys. Okay, go ahead. I'm ready, Trudy.